Bienvenidos a la Universidad Militar Nueva. Bienvenidos a la Universidad Militar Nueva Granada. Preste atención a las siguientes recomendaciones importantes en caso de emergencia. Atienda siempre las instrucciones del personal de seguridad y brigada. Son quienes le indicarán qué hacer en caso de presentarse cualquier evento. A ellos puede informar acerca de cualquier anomalía que usted detecte, o en caso de presentarse alguna emergencia médica. Usted se encuentra en el Auditorio F. Identifique la salida más cercana a usted. Estas se encuentran debidamente despejadas y señalizadas. En caso de sismo, mantenga la calma. Permanezca en el sitio hasta que pase el sismo. Ubíquese en posición fetal frente a su silla. Hágalo doblando el cuerpo pegado a las rodillas y ubicando las manos detrás de la nuca. Solo en caso de que la evacuación sea inminente, se activarán las alarmas de evacuación tipo sirena o silbato, las cuales sonarán indicando que se debe evacuar. En caso de presentarse conato de incendio o si percibe humo en el recinto, evacúe el sitio cubriéndose la boca y nariz con un pañuelo o su mano. En todos los casos, esté siempre atento a las indicaciones del personal de seguridad y de brigada de la universidad, quienes lo guiarán hasta el punto de encuentro ubicado en la zona verde posterior al auditorio. Para su tranquilidad y la nuestra, la universidad cuenta con los recursos necesarios para la atención de posibles emergencias. Estamos preparados y seguros de que su permanencia en nuestras instalaciones será de su completa satisfacción y seguridad. Recuerde, ante cualquier situación de emergencia, mantenga la calma, porque la clave de la seguridad somos todos.
Buenos días. Estamos aquí para la exposición del profesor Christophe Chauvin del Departamento de Física de la Universidad de Montpellier. Él es el líder del grupo de metrología cuántica del laboratorio Charles Coulomb de la Universidad de Montpellier. Y pues él es profesor universitario ya hace años. De hecho, yo lo conozco, nos conocemos desde hace más o menos unos 22 años, cuando yo estaba haciendo mi maestría en la Universidad de Montpellier. Y pues él fue mi director de tesis cuando yo estaba en maestría. Entonces pues lo conozco yo ya desde hace bastante tiempo y desde esa época hemos seguido trabajando en temas de investigación, en particular sobre fenómenos relacionados con lo que es el efecto Hall cuántico y el efecto de los cables en la medida del efecto Hall cuántico. Entonces ese ha sido como el tema que hemos manejado nosotros durante los últimos años y pues el profesor hoy les va a hacer una exposición sobre el nuevo sistema, las nuevas definiciones de las unidades en el sistema internacional. Entonces, pues de pronto ustedes no lo saben, pero desde 2019 se cambiaron las definiciones de las diferentes unidades partiendo del kilogramo que se volvió a definir a partir de, digamos, constantes universales. Antes, digamos, había una manera de hacer las medidas, ahora pues todo está basado sobre fenómenos que tienen que ver directamente con la mecánica cuántica y también pues relacionan las constantes universales con las unidades de medida. Entonces, le cedo la palabra aquí al profesor.
Thank you very much, Carlos. I will speak in English because my Spanish is not as good. And I would like first to thank the university here and all the colleagues of the physics departments that are receiving me very well here since I'm here in Bogota. Well, thank you very much. So let me first introduce my small team in Montpellier, where I work in a big lab, which is like 150 researchers and 300 people. But we are separated in small or medium team. And for example, we are four. Adrien Delgar, he has now left the group. He was first he was a PhD and then a postdoctorate. Our research concerns the electrical quantum transport, basically, and quantum phenomena. But we work since a long time in link with the problem of electrical metrology. And we work also on the high electron mobility transistors and on the measurement techniques and precisely on the effect of coaxial cables on the measurements. That means that we have some experimental facilities like cryogenic environment and high magnetic field that I will present you quickly. I will not present how we process semiconductors in clean room, but this is done essentially in Paris, in Center of Nanoscience, and in University of Tokyo. And we work also with precise and low noise electronics, but I will not present you that either. Our collaboration for the sample here, I collaborate with UNS de Lyon for theoretical and with your university, with Carlos, since a long time. And I collaborate also since a long time with French Metrology Office in Paris. So we are physicists, we are not metrologists. And just to say that the sources of this talk have been taken from the PhD of two students, Jérémy Brun-Picard and Jérémy Guignard, which have been in Saclay, and in which I was an examinator. So most of the precise measurements you will see in this talk are taken from this PhD thesis, which are written in French, actually, not in English, but are accessible on the internet. Some picture I taken from Bureau International des Poids et Mesures. I don't know if you know this international committee, which is in Paris since 200 years, but which is an international committee whose aim is to harmonize all the metrology of all countries around the world. Laboratoire National d'Essai is precisely the French metrology, so it's different from the BIPM, and it is near Paris also. I will present some of our work just to make you catch the physical phenomena on which we are working, and of course I will use scientific literature. So the outline of my talk is quite simple. I will present two macroscopic quantum effects, which are the quantum Hall effect and the Josephson effect. But during this talk, I will present you also the techniques. This is two instruments, the Thomson-Lampard capacitor, which is necessary for the new definition, and the force that I will present you. And these are technologies, the Josephson junction array, which is high technology, which is done in clean room, and the quantum Hall bar, which are also processed in the clean room. So I will make an overview of all these techniques. Until 3 years ago, the Ampere was based on an artifact. That means that you have to measure a force to realize 1 ampere. If you have two infinite wires, then you have this force between wires if they are separated by 1 meter exactly. But this is a force by unit length. So it is very difficult to measure because you never know on which length it is applied. And besides, you never had infinite wire. So it is a problem, and the precision of this experiment have never been better than 10 to the minus 6. So since 2019, now the definition of the ampere is this. It is not defined as an ampere, it is defined for the electric charge. The elementary charge is exactly equal to this number. And as you know exactly the electron charge, then you can realize 1 ampere. How do? You take those two macroscopic quantum effects, because the voltage standard is defined since this date with the Josephson junction, and the resistance standard since 30 years now is defined using the quantum Hall effect. And you just realize the Ohm's law with those two standards of voltage and resistance. Okay, so this I will present you, and how do you realize this Ohm's law, basically. Yeah. So before 3 years ago, you could measure the electric charge. You could measure the Planck constant, the Avogadro number, and the Boltzmann constant. You will see that now this is fixed, the electron is fixed, and all those constants are now are now fixed by decision. So this is the standard, the units before 2019. Only the second and the meter have a special status and based on quantum effect. The second is based on the radiation of cesium, and the meter is defined by the light celerity. But for the kilogram, we still have, until this date, we still have an artifact. And it is the same for the three here that I will not detail. So let's first explain what happened to the meter in 83. Before 83, we had an artifact. This is not this one. This one, one of the first artifacts, which is still visible in Paris, on the wall of the Seinat. It is, you can touch it. It is still there, and it was in the street because people need to have a reference easily accessible. So it was in the street, and since this date we have fixed the speed of light, because what happened is that we measure the second much better than the meter. So now the second is very well defined by atomic clock. So you can measure the distances by using the speed of light, which is fixed by decision again. So this is the same thing that appear to happen for the ampere. The same process that we fix the electron charge, and then we measure the ampere. But first, let me present you one of the instruments which allow this definition, which is usually not known, which is a Thomson-Lampard calculable capacitance. And it comes from a very old theorem of Mr. Thomson and Lampard in 56, which tells you that if you have 4 cylinders, metallic cylinder like that, and if you put a 5th cylinder inside the 4th, then depending on the position of the 5th cylinder, you can calculate the capacitance. The theorem tells you that it is exactly this value. And this value is known as in fact, what you know is for displacement. This is you have a capacitance per unit length. So if you can measure very precisely the displacement, then you know very precisely the capacitance. And this is an instrument which has been built in many metrology labs around the world. There is one in Paris, one in Berlin. There is not so much, but there is some of these apparatus which are quite complicated to handle. As you see, what you need, in fact, is a cylindricity and parallelism very, very precise. And actually, the precision is 1 micron on the cylindricity and the parallelism. And it is done by hand. Those cylinders as done by hand, just by, I don't know the name in English, but polishing. Yes, by hand. So I saw a guy when I was there once who came with 1 cylinder just to measure the cylindricity. And this guy was doing it by itself, but for months, polishing the cylinder. So now you have now we have a calculable capacitor. Sometimes it doesn't work. We have a calculable capacitor, which is based on the meter, and so you can relate the capacitance to the second, because the meter is based on the second. And you have also precise for all the, since very long time, we have frequency generators which are very stable, and you know very well the frequency because they are synchronized with atomic clock. And if you use a bridge, that means that you can measure precisely a resistance. And that's what happened to the quantum Hall effect. The resistance of the quantum Hall effect could be measured very well using a bridge, an AC bridge. And since in 1988, la conférence CIPM is la Conférence internationale des poids et mesures, decided that the quantum Hall effect was a resistance standard. Okay, 1 semiconductor samples could make the resistance standard, and those old very stable resistance, which are cadmium resistance, which are conserved in an oil bath at a very stable temperature, give very good result, but in the long term, there are deviations that exceeds 10 to the minus 6. And the quantum Hall effect is based on fundamental constant and is not deviating. So let me now present you the quantum Hall effect, how could we make a resistance standard with this. So we take a sample which is semiconductor and a heterogeneous structure. So that means that you grow it, this is the growth axis, you grow it atomic layer by atomic layer in a molecular beam epitaxy. And then you monitor the presence of aluminum. And so when you stop aluminum, you have here a quantum well, which is represented here by what you see on this picture here is the conduction band of the semiconductor. And there is a quantum well, and in the quantum well you can see the wave function of the electron, which is confined near the interface with a scale of about 20 nanometers and cannot escape. That's why electrons can move only in a plane, and was that we call a 2-dimensional electron gas. there is a disorder potential. There is a disorder potential which is caused by the impurity you have added here to populate the quantum well with electrons. So, and this impurity ionized, so electrons live in a disorder potential, which is in fact necessary to have the larger plateaus in the quantum Hall effect. I will show you. So on this two-dimensional electron gas, we applied a high magnetic field, and this high magnetic field gives you, makes the electron live on an energy ladder, which is called the Landau levels, which in fact equally spaced, because an electron in a magnetic field is an harmonic oscillator, and the energy level are equally spaced. And if the energy space here between two levels is larger than the temperature, then you can see the effect of quantization in those structures. Because of the disorder potential, the width of the Landau levels widens, so we don't have like Dirac peak, but we have like smooth Landau levels. And in the middle, we have delocalized states. That means that electrons can flow from one contact to the other through the sample. But on the edge of this Landau level, we have localized states, and that provokes the width of the Landau levels, of the plateaus. We have to cool down the samples, and we use a cryostat, an helium-4 cryostat, in which we have a variable temperature inset, which allows to monitor the temperature between 1 Kelvin and 300 Kelvin. And so we use a rod that here, that makes the interface between the samples down in the superconducting coils. This is the superconducting coils here. So the sample is in the center of the superconducting coils. And what you see here is the head of the rod with cables that goes from here, here's the sample, up to the top, and then connect it to the instrument. And we just take the whole bar here, you can see here, which is connected to the sample holder with very thin gold wire, and plug here on the central rod. So what do we observe? What do we observe? We observe that we measure two things. We measure the longitudinal voltage, VX6, and we measure also the transverse voltage, which is the Hall voltage, VH. And what you observe here is some plateaus. Instead of having a linear Hall effect, you have an Hall effect having plateaus. And those plateaus, the value of those plateaus, are directly related to the quantum conductance, to the quantum of conductance, which is E square over H. So here, if you measure the resistance, you have H over 2 E square. When there is 3 Landau levels filled, then the resistance is H over 3 E square, etc. So you can measure a resistance which is linked directly to the fundamental constants and to some integer. And that's why the quantum Hall effect is very stable. And it is a macroscopic quantum effect because you observe it on sample. This sample is 1 millimeter long. So it is not something very small. It is 1 millimeter, so it's macroscopic. But nevertheless, you observe a quantization of the Hall resistance. And this happens when the Fermi level is just between two Landau levels. So that's why you have here a plateaus, and these plateaus allow you to make a good measurement because you don't have to fix very precisely the magnetic field. You have all a zone, you have a zone where you can have these results. So this is not enough to define a resistance standard. What you need is to compare resistance. You have to compare the Hall effect in Paris to the Hall effect in Berlin or in New York. And you have to compare it with this kind of precision. So that's the first thing, and I will show you what is the key instrument to make such a precision in comparing resistance. And secondly, you have to measure it, and to measure resistance, we use, metrologists use a bridge which is an AC bridge with alternative current, and the resistance here of the whole resistance have been measured since this time very precisely using an AC bridge and the Lampard. Before continuing, let me make a first parenthesis on what are we working on in relation with this metrology lab. So what you see here is how the quantum effect is destroyed by the temperature. All these experiments are the same, but each curve corresponds to a different temperature. So the smaller temperature gives you the larger width of the plateaus. And so here on this picture, the lowest temperature is 1.3 Kelvin. And the higher temperature that you can see that it suppresses completely the plateaus is 30 Kelvin. So at 30 Kelvin, you have destroyed the quantum effect. At 1.3 Kelvin, the quantum effect is reliable. Another subject on which we have been involved in collaboration with the French Metrology Office is the effect of the current. What you see on this picture is that the longitudinal voltage here, which is vanishing, if you increase the current, then the longitudinal voltage does not vanish anymore. So the quantum effect, the quantum phase is destroyed. And that is what we call the breakdown of the quantum effect. And so for each sample, you have a critical current over which that tells you that you don't have to overpass it. If not, you destroy the quantum effect. And why it is important? It is important because metrologists know since a long time that the whole resistance is affected by the presence of a longitudinal resistance. So you have to handle the current very well and not too high to have a good measurement. What we have done here in this experiment is we have shown that in fact the electron phonon was responsible of this breakdown of the quantum effect, and what you see here is that the breakdown is in fact an exponential increase of the longitudinal resistance. It is not hazardous. It is very well defined, in fact, and you can reproduce these curves by calculating the electron-phonon interaction. What was useful also for the metrologists is to know how the critical current scale with the width of the samples to make them widen or shrink, in any case, to find the good width for the metrological samples. So this is the end of the parenthesis. Let me come again on the measurement and the comparison of the resistances. So let me present you a second very useful instrument which is built by hand in the metrology lab all over the world. If you go to Berlin or to Paris, you will find such a 4C, a cryogenic comparator of continuous current. So what is this small thing that you can have in the hand? It is not very big. You can even put it in, you have to put it inside the cryostat because it is a winding. You have to winding the wires, and those wires are recovered by a superconducting shield. So if you want to compare two currents in two wires, you wind one wires in a sense, and the other one in the other sense. And you recover everything using a niobium, I guess, a niobium shield. But in a certain manner, you roll it not hazardously. You roll it in a certain manner such that it is very well recovered. And inside, you just install a squid to detect the magnetic field. So how does it work? it works. This is a piece. This is a piece of the door in which there is two wires. So let's say that there is this current is N1 times the first current. N is the number of turns, and E is the current. And on the other wire, you have N2 times the high 2, the second current. And because this is superconducting, if the current are not equilibrate, then you have a current, a surface current, in the inner side of the superconducting to equilibrate the current inside and make the magnetic field vanishing in the superconducting. Because it is rolled in a certain manner, you recover this current on the top face, on the outer face of the superconductor, and then you have here, you are left with a current that goes on the surface of the superconductor, and because there is a current, there is a magnetic field, and because there is a squid which detects very finely the magnetic field, you can detect like one quantum flux in the squid. So that means that because N is very big, and the number of turns is very big, so you have a precision then of this order. So this is a key instrument of the metrologist to compare two current and make bridges very, very precise. So what do metrologists? They compare, in fact, two different samples. They compare even samples in gallium arsenide with samples in graphene, and they compare samples from Paris to New York by using they use what they call the standard that they can travel, and they compare it in Paris. They took the standard of comparison, they took it to New York and make another comparison in New York. And what you find here, this is the results in Paris, Switzerland, Germany, England, and US. And you compare the value of the whole resistance at this relative precision, 10 to the minus 9. And you observe that, in fact, it is precise to this precision. So this is the first step to make a resistance standard, is to compare all over the world the different experiments, different samples with different electron density, but which all gives the same h over e square. The second step is to measure the value of the resistance RK there, and you do it using the Lampard with an AC bridge, and you compare the resistance with a capacitance by using a very stable frequency source. But doing this, metrologists have shown that since a long time that when you use an alternative current, then the plateaus, you see here is a magnetic field, and the plateaus is not flat. It is modified by the presence, by the AC current. In continuous current, it is very flat, but in AC current, it is not flat. And you can see that if you increase here the frequency, then the flatness is even worse. So there is two reasons for the deviations of the all resistance from this from the expected value. One is the presence of the coaxial cables that modify the measurement, and the second is the presence maybe of inner capacitance of inductance inside the samples. So this is one of the subjects. I make here a second parenthesis on our work, what are we working on in link to this metrology. We have been working with Professor Carlos Hernandez on the effect of the coaxial cable on this measurement. And for example, in this picture, what you see is that the conductance of the whole plateaus is modified according to the number of coaxial cables you have in the system. this is one of the first things. A second thing is we observe also quantum inductances. I mean, there is classical inductances, but in quantum system, you have also quantum inductances, because what is an inductance? An inductance is something where you can keep energy, and you can keep energy in a solenoid. For example, in a classical solenoid, you keep energy in magnetic, in the magnetization of the, and in quantum system, you keep energy in in populating upper states, and then you keep energy in the quantum energy levels. So that we have shown recently, and what you see here is that the more the length of the edge states of the quantum Hall effect, the greater is here the quantum inductances. The order of magnitude is some tenths of microhenry, which is not very small, so you can measure it. And you can measure it because the samples are big. As you can see here, from this contact to this contact, it is nearly 2 millimeters. So it is macroscopic. And you observe this. And what you observe is why it is quantum, why you know it is a quantum inductance. Because you see here, it is the number of field Landau levels. So here there is 2 Landau levels. Here there is 4, 6, 8, etc. So the more Landau levels, the less the quantum inductance is. So let me now finish with this parenthesis and explain you the second macroscopic quantum effect, which is used to define the Ampere, which is the Josephson junction. Josephson was a Nobel Prize in 73, but his article was 10 years before, in 62. And okay, I'm not specialist of superconductors, so I can only give you some small things. I will not be able to respond some questions on the Bose condensate of Cooper pair that exist in the superconductor. You know that electrons are linked by two due to the phonon interaction again, and they propagate as a pair that we call Cooper pair. And because the Cooper pair of electrons are bosons, they condensate in one macroscopic quantum states, which is represented here by this wave function. And what we are interested in is the phase of the wave function. And on the other side, you have a second superconductor. And you have here the second phase, the phase of the second state. And in between the two pieces of superconductor, there is an insulator. And what you measure is the tunnel current between those two superconductors. And the tunnel current, it is shown that the tunnel current varies as a sinus. And the phase is a difference of phase of the two macroscopic wave functions. And the difference of phase of this macroscopic wave function has been shown by Josephson, and it is the Nobel Prize, that it is proportional to the voltage, inversely proportional to the quantum flux, and proportional to the time. So that means that if you apply a continuous current, then you a continuous voltage, then you observe an AC current. And there is another effect, which is linked to this Josephson effect, is now if you apply an irradiation, an electromagnetic irradiation at a certain frequency, I mean an AC voltage, then what you observe is a continuous current. You know, so now if you irradiate here with an electromagnetic radiation, then what you observe is a continuous voltage as a function of the current. So this is the IV characteristic of the Josephson junction, and when you observe what we call the Shapiro plateaus, and again, because you have plateaus, you can imagine making a voltage standard, because you can measure this plateau very well. And those plateaus are given by the number of Josephson junction in the array, the quantum flux, and the frequency of the electromagnetic waves which irradiate the array. This is a zoom here on top of the slide. This is a zoom of the Shapiro Shapiro scale. You observe that it is very well defined, and for this very stable voltage generation, it is now 30 years that it is the voltage standards. Before this time, the voltage standards was like battery in an oil bath with precise temperature holding, and finally, what you see here is from several institutes around the world and several years. This is different measurement of the voltage standard. Here, this is a 10-volt standard, and the deviation is nanovolt. So you see that you have a precision with the Josephson effect, which is 10 to the minus 10. So now you have voltage standard, you have a quantum Hall effect standard, a resistance standard. What you can do is just applying the Ohm's law. So you take the voltage given by the Josephson junction when you irradiate it with a certain frequency. So the frequency is here. This is the flux quantum. And Ng, the number n is just the number of array, the number of junctions in the array. So usually it is like 7,000. You see here you have 7,168 junctions, and this is the number that you have here. And the current, which is the voltage, create a current in the old resistance. So now you can measure the current as a function only of the electron charge. Fg is the frequency of the generator, which is very well known because the time is very well measured. Ng is an integer. So the current is just depending on the electron charge. So if you fix the electron charge, now you have you can measure very well the ampere. Why? Because the flux quantum is h over E. The resistance is x squared over h over E squared. This is E over h. So at the end, you have only the charge of electron. In the thesis of Jérémy Guignard, in which I was in Paris, he built a small system. I mean, not as heavy as the one that we have in Montpellier, which is a big cryostat, 2 meters high. But now in this kind of company, cryomagnetic company, you can buy an helium-free cryostat that gives you maybe not 16 Tesla, but if you choose a graphene sample, then you need only 4 or 5 Tesla, it's enough. So in this kind of commercial, cryostat, helium-free, you can handle not very easily, but quite easily, a standard of current. And this is the measurement which have been done by Jérémy Guignard in his PhD thesis, and you see that it didn't reach 10 to the minus 10, but he reached 10 to the minus 8, which is relatively sufficient to make calibration of any commercial amperemeter or voltmeter. So, to finish, what happened to the ampere has in fact happened also to the other units and to the other fundamental constants. So now the electron charge, but also the Planck constant, the Boltzmann constant, and the Avogadro number are fixed by decision. We decided that. And from this fundamental constant, for example, for the Planck constant allows you to define the kilogram. In the same manner that the speed velocity, the light velocity defined in the meter, and now the electron charge defines the ampere, the Boltzmann constant defines the Kelvin, and the Avogadro number defines the mole. So that's the new definition since 2019. that has been blurred by the pandemic. So nobody of us, of physicists, are aware of that, because in the last 3 years we were thinking about something else. And but it is very, I mean, it is quite a revolution, because now you don't measure the electron charge, you don't measure the Boltzmann constant. They are known, and they are used to define the units of the physics. The talk is finished, but I have 3 more slides on for the kilogram, because yesterday I had a question on the kilogram. So let me finish, because it is interesting how the kilogram is related to the Planck constant. And in fact, this is a really, it is really new, because in fact, first, why it is not completely, why the kilogram, the artifact, is not a very well solution, a very good solution. Because in fact, the artifact, it's moving. I mean, it's changing. The mass is changing. Why? Because atoms are just stacking on the surface or destacking. So the number of atoms on the kilogram is moving. Even if you keep it in the vacuum, even if you keep it in very good condition, it is moving. And that's why what you see on this picture, it is moving in 100 years of 10 to the minus 8. And so this is for the primary standard. But for the secondary standard that travels, it is worst. So you need a good kilogram, and you need also to make a link between the electrical units and the mechanical units. For example, what you need is the power. The electrical power must be the same as the mechanical power. And you do that with what we call the Keeble balance, so the Keeble balance, there is very few. This is the one in Paris, there is one in New York. Maybe there is 3 or 4 in the world, or maybe 5 or 6, but very, very few. It is very difficult experiment to handle. And what is a Keeble balance? In the university in France, we call it la balance de Coton. I mean, Mr. Coton was the guy who first showed that you can equilibrate the gravity with an electric force. And this is the basic principle to make the equivalence between electrical units and mechanical units. So the Keeble, who were metrologists in the US of the NIST, National Institute of Standard, have found that in fact, what is not very well known here is the length on which the electric force is applied. So the idea of Keeble was to make 2 different experiments, one static and one dynamic. And then, because the length here of the conductor is in both experiments, then you can eliminate this length, which is in fact the poor precision in this experiment. And so now, if you have the 2 experiments, you see that the current here is a voltage divided by resistance. And if you use here for the voltage the Josephson effect, and here for the resistance the quantum Hall effect, then you can relate the mass with those 2 numbers, which is the fixed quantum and the Hall resistance. But now there is a square. This is kg square. So now that it is the electron charge that disappear, and you are left with a Planck constant. So now we can relate the mass to the Planck constant. As it is strange, but it is like that. And here, the number here is just a number of the Josephson array that is used to measure the voltage, and the frequency here is the frequency of that you irradiate with which you irradiate the Josephson array. And that's all. Thank you for your attention.
Thank you very much for your presentation. Very nice, very illustrative. I still wonder myself because we are measuring quantum things through macroscopic things. So still, we have that barrier. And in one of your slides, you presented this Josephson coils. It looks like oh, thank you. For the Josephson coil, it looks like I see like a transformer. So two kind of winds. With
Well, yes.
yeah,
There are transformers.
yeah, but the point is, for instance, the cables going out from those windings, they are like twisted. And the distance, also, how long are these cables? Because they behave like a transmission line. And maybe the efficiency for cable longer than 1 meter is very low. I don't know, maybe you know for sure. How does it affect your measurements? For instance, those cables on the upper side, like the blue or green, they are twisted.
Yeah.
So that distance, so all those cables, they behave like a transmission line, and they have a proper impedance by themselves. How long is that distance?
Those distances, because you put this inside the cryostat, so it is quite long. But the thing is that the comparison is made in continuous current. The use of alternative current was to measure the quantum resistance, h over square, until 2019. And this is what you observe here. So this was, I think the last measurement was in 2018. So they decided, okay, the measurements are good, so we don't measure anymore. So we just realize the ampere. Just to say you that the problem is when you measure in alternative current.
Yeah.
And this is a hard subject on which metrologists have worked during 20 years until they've done this kind of measurement, just to be sure that the resistance was exactly h over square.
Okay.
And then it is a decision. We decided that. And what you have to do is to take now a continuous current to realize the ampere through Johnson.
Okay, thank you.
So it is a very good question. And they have under that, by stopping, okay, now we stop IC current, we measure it in continuous current.
Okay, thank you. Maybe I was missing this part because I wonder if we work with high frequency, like it's in the range of microwaves, I think. Yeah, for sure.
It is a real problem.
Okay, thank you.
And that you can see here. I mean, this is just an example, but we have worked with Carlos on this subject. And there is a lot of literature, and it is a real mess. I mean, because there is not only the cable, but there is all the connectors. The connectors that have a frequency behavior. So you have to take it into account.
Okay, thank you very much.
You're welcome.
¿Alguna otra pregunta? Ninguno. En español, no importa. Bueno, pues le damos las gracias al profesor Sobe por su presentación.
Muchas gracias. I'm very pleased to be here. I hope I will come again. Okay. Thank you very much.
Muchas gracias a todos por su asistencia.